In the dark times, we had cathode ray tube screens. They worked poorly, and we suffered from the cruel dictatorship of low-quality images. But in the 1990s came the light, LED light. LED backlit liquid crystal displays, or LCDs, used LEDs to shine light through an LCD panel, giving us better brightness levels, contrast ratios, and thinner screens. And then came OLEDs. Carrying their own backlight, they offered many improvements and foldable screens too. But for all their current dominance, the technology still has significant drawbacks. Threatened, the LED manufacturers developed mini-LED displays for things like your iPads. It looked better, but not enough. So, the display manufacturers looked for a way to gain all the benefits of OLED and LED backlit LCDs with none of the drawbacks. In this video, let us talk about micro-LED technology, the prince that was promised. Micro-LEDs represent a paradigm change from LED backlit and mini-LED displays. They're more like the big outdoor screens we see all around. Such outdoor displays use standard-size LED chips as their pixels. These chips are about 300 by 300 micrometers large. At that size, the human eye can make them out when they are close, which affects the viewing experience. But it works for an outdoor display because most people are viewing them from far away, and the LEDs can get bright enough to be seen in daylight. In order to make LEDs pixel suitable, they have to get smaller. Displays with chip sizes of the range 100 micrometers by 100 micrometers, or smaller, can be considered micro-LEDs, but of course definitions vary. Theoretically, micro-LED displays can match up with OLEDs on many of their features. Because we remove a polarizing layer, the display can get much brighter than an LED backlit display, with amazing response times and very wide viewing angles. They can offer high contrast ratios and low power consumption, and since their materials are not organic, they enjoy longer useful lives. And since we can attach them to a flexible substrate, they can be made foldable too, just like with OLEDs. People envision using these for consumer items like smartwatches, VR displays, and microprojectors. Scientists have been mulling the possibility of a micro-sized LED screen basically since the invention of the blue LED in the early 1990s. And of course, the concept of outdoor LED screens have been around for a while. In 2000, a technical group at Texas Technical University announced the first micro-LED quote-unquote display. It was just a 10 by 10 array of chips, but each of those chips was just 12 micrometers large. Even so, the display demonstrated some of micro-LED's tantalizing benefits, like nanosecond response times. At the 2012 Consumer Electronics Show, Sony debuted a 55-inch fully HD micro-LED TV, equipped with 6 million micro-LEDs. Compared to its contemporary LCD and plasma displays, the micro-LED display offered 3.5 times better contrast ratios, 1.4 times wider color gamut, and 10 times faster response times. Then in 2014, Apple acquired a stealth company called LuxView, which had been working on micro-LED display technologies. Analysts thought they were going to use them for their Apple Watch. Apple ended up using OLED screens for that device, but whenever Apple buys any technology, it turns heads. So in 2016, Oculus, owned by Meta, acquired an LED manufacturer called InfiniLED. Oculus then partnered with the micro-LED startup Plessey Semiconductors to build such a screen by 2020. Micro-LEDs are one of the more promising VR-enabling technologies out there, a potential holy grail. Backed with investments from Sharp/Foxconn, Google, Intel, and Samsung, a plethora of micro-LED startups like Jade Bird Display, Lumiode, and Plessey have launched, slowly making their way towards selling actual products. In 2018, LG, Samsung, and Play Nitride, a company in Taiwan, demoed their micro-LED-based panels. I should note that Samsung's 146-inch screen, dubbed the Wall, I guess after Game of Thrones or something, uses chip sizes larger than 100 micrometers, which does not classify it as a micro-LED screen. Anyways, There is a lot of money sloshing around in this space, and companies are actually starting to launch a few products here and there. As of this writing in 2022, you can buy an 89-inch micro-LED TV from Samsung for a smooth $80,000. With that in mind, however, the technology has yet to fulfill its great expectations, and that is largely because of how hard it is to manufacture. The process of making a proper good micro-LED screen starts with growing these very small individual LED chips in their red, blue, and green colors. The most direct way to do this is to grow these chips like crystals, a style the industry calls epitaxial growth or just epitaxy. These are done on wafers made of sapphire, yes, the precious gemstone. This can be done with either chemical vapor deposition or molecular beam epitaxy. The first is where you use a chemical vapor to create a thin layer of some material onto another. The second, molecular beam epitaxy, is where you fire thermal beams of molecules at a substrate to create your thin layer. Of the three RGB colors, micro-sized green and red chips are particularly tricky to produce at mass scale. Blue and green micro-LED chips are mostly grown with indium gallium nitride. Blue chips have also been made using gallium nitride. Manufacturing green micro-LEDs is harder than blue because of the indium. Growing such an LED chip with high levels of indium gets harder as the wavelength gets longer, i.e. from blue to red. There are a number of reasons for this. First is that the spacing between indium nitride and gallium nitride atoms are mismatched, something called lattice mismatch. When mashed together, this creates dislocation defects. Second, indium is unstable at higher temperatures, so micro-LED chips with higher levels of indium have to be grown at relatively lower temperatures, of about 600 degrees Celsius. Yet, these same lower temperatures can lead to crystal quality defects. Too many defects jack up the cost of fabrication. So, manufacturers have to compromise with middle temperatures, striking a balance between two bad situations. And then there are the red chips. Red light has an even longer wavelength than green light, so if you want to grow them using the same indium gallium nitride, then the indium content has to be over 35%. It brings up all the same problems we talked about before, but worse. So okay then, how about we just shrink existing sized red LED chips? But it's not that easy. Normal sized red LEDs are grown using aluminum gallium indium phosphide. These types of chips have a significant size energy efficiency problem. As LED chips get smaller, the amount of emitted light you get for the power you put in starts to decline. The ratio measuring this is called external quantum efficiency. How many photons does the LED emit for the number of electrons passing through it? Efficiency falls because large defect areas start appearing inside the chip. In these defect areas, known as Shockley-Reed-Hall recombination sites, the electrons in the chip's molecular structure do not release photons as they normally should. That's the best way I can explain it without a dissertation. Anyway, these defect areas actually happen in chips of all sizes, but are far more noticeable on a very small chip. It's like a big mole on someone's face. Shrinking a chip from 100 by 100 micrometers to just 20 by 20 micrometers can mean losing 60 to 70% of its external quantum efficiency. Red chips are particularly vulnerable to this effect because of the inherent properties of aluminum gallium indium phosphide. Researchers have been working on several workarounds. There are compromise solutions with quantum dots that I won't cover. The less this video uses the word quantum, the better. But progress towards making red micro-LED chips with indium gallium nitride is promising. Let's hope they come through. So making the individual micro-LED chips is hard, but people don't even consider that to be the hardest part of the whole micro-LED commercialization endeavor. Because after that, you have to transfer these individual micro-LED chips from the 4 or 8 inch wafers on which they are grown onto the display. Depending on the LED chip size, 2K 6-inch mobile phone screens have 11 million chips that need to be placed. A 4K display panel will have about 25 to 30 million micro-LED chips. An 8K panel, 100 million chips. All of these chips have to be transferred over from their wafers and placed extremely quickly, 100 million chips an hour to be economical, and extremely accurately, literally down to the micrometer. Oh, and it needs to be cost effective. Can't forget about that. After that, you will need to find a way to QA and repair errors, because there will be errors. Even if your mass transfer technology works 99.99% of the time, that means you have 2,488 damaged pixels on your 4K screen. Existing technologies have demonstrated the feasibility of their methods on mini displays 1 to 2 inches large. Can these methods scale? The industry has explored a number of strategies for conducting this mass transfer. For this, I'll go over pick and place, electrostatic, fluidic self-assembly, and roll-to-roll. Spoiler alert, right now none of these methods can meet all three of our goals: high speed, high accuracy, and low cost. Pick and place is what the LED industry has traditionally used. A machine literally picks the chip off the wafer and then places it onto the display. Obviously, the issue is that with micro-LEDs, you have to deal with more chips that are far smaller. It takes longer, and you might damage the chip. Even if you can pick and place 1 million pixels an hour, that's 11 hours for a single 6-inch phone screen. How can you deliver 200 million phones, which is how many iPhones were sold in 2021, that way? Electrostatic is a promising one. It was proposed by LuxView, the startup Apple acquired back in 2014. You use an electrostatic force to pick up the chips like nails to a magnet. Then you release the voltage and drop the chips onto the substrate. It works, and LuxView demonstrated a panel assembled with it, but there are concerns about chip damage. Fluidic self-assembly is kind of wild. You use photolithography to etch holes on the display substrate. At the bottom of the holes are bits of aluminum chromium tin. Then you wash the LED chips off the wafers in a liquid and pour the liquid onto the substrate. The chips will fall into the slots via the capillary effect, which you then bond to the chips using heat. It works at a high speed and doesn't require expensive equipment, but the transfer yield is poor. And finally, we have roll-to-roll. It was first demonstrated in 2013 by the Korean Institute of Machinery and Materials, or KIM. It is much faster, about 36 million pixels an hour, but the accuracy has some troubles. You will soon see why. You take a roll coated with some suspension gel and roll on the TFT control circuits first. Then you roll it over the wafer with the micro-LEDs. The micro-LEDs will attach to the control circuits. Then you finish up by rolling the now completed LED and control circuit roller onto the final display. This process makes me think of stacking together Legos with a sticky pet hair roller. You can guess why this might have some yield issues. Researchers debate amongst themselves about which of the mass transfer methods I mentioned, and others that I haven't, is the right one to use. Lots of these work, but can they work well enough to offer compelling price advantages over existing display technologies? While there are some ways to lower the cost of manufacture, like using larger wafers to grow the chips, the technology remains very expensive. And the crazy thing about all these micro-sized technical challenges is that we probably need these chips to get even smaller, beyond 10 square micrometers perhaps, in order to produce them at a scale suitable for mass commercialization. MicroLED has long been said to be coming, and each little breakthrough is hailed as another step towards making such displays become a reality. But after a while, the public just gets tired of hearing it. Considering the substantial technical challenges that vendors have yet to conquer in commercially feasible ways, I wonder if micro-LEDs might be one of those technologies that is always just a few years away from being in your hands. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.